Okay, so the question becomes then, why do we need this? I mean, we have a perfectly good XYZ axis system. Why would we need to convert things to cylindrical? And the answer is something like this one right here that we're about to do, because this would be awful to try to integrate with respect to x and then with respect to y with those kind of limits of integration, and that is your integrand. Ugh, ugh, ugh. You convert to cylindrical because it's going to be easier. All right, so let's first look at this region for just a second. Now, don't look at this, right? This is some density, if you will, of this three-dimensional object. We don't have a good way to graph that. We don't know what that looks like. But we do know what x equals square root of 3 times y looks like, right? That's a line, right? MB, right? And then, or mx plus b, but it's reversed. And then this would be a semicircle, right? So let's look at this actually in Desmos. I built it in Desmos right here. So you've got your semicircle, which is the purple one, right? The square root of 1 minus y squared. You have your diagonal line, because that's the square root of 3 times y, right? That's the diagonal line. And you want x to go from one to the other. And you also want y to be from 0 to only, I think, a half or something like that, but it'll be fine. So 0 is less than or equal to y, which is less than or equal to a half. So you're in here, in this wedge zone right here, which, by the way, if I make it so the y is less than or equal to 1/2, you'll see that doesn't change it one bit. So we're good. Okay, so let's draw that. So I'm going to draw that piece. So we have the circle, really the semicircle, that's all I really need. But I can do the whole thing, right? So that's what x equals the square root of 1 minus y squared is. It's a semicircle. Right? Okay, and then x equals the square root of 3 times y looks like this. It's a diagonal line. And so I want to be in this zone right here, right? This is where I'm going to integrate. And that's all I'm really considering. I don't need the three-dimensional object in this case. It wouldn't help me. It's some surface. I mean, I can show you what it looks like, but it's not really relevant for us. But keep in mind, the surface does not come from this piece. It comes from z equals -1, z equals +1, y goes from 0 to a half, and then x goes from the, right? So it's not in there. It's actually like a cylinder kind of stacked up in here between -1 and +1 for z. Right, that's what you're looking at. So imagine this piece, but stretched out vertically up in the air and backwards down into the table. That's what it is. So it's like a big piece of cake, essentially. Right? If this was a big tall cake, right? And you're looking at it from up above, and there's the center of the cake. Okay, so because this is not that, right? This is density, right? This is its own thing. Okay, so let's start by finding, and I'm actually going to segment my paper off so I don't run into trouble with my conversions here. All right, so I'm going to rewrite this triple integral. I'm going to start by rewriting this as the square root of r squared. All right, so that's the square root of r squared. And I'm going to convert it. So it's times r, and then dz, dr, d theta. Oh, and I want to use different colors. Sorry. Okay, so dz will be in green, dr will be in pink, and d theta will be in the light blue. Okay, so, oops, theta. There we go. All right, so z is easy because z doesn't change. So the z's were right here, right? They were in the last one, so I'm going to move them to the front ones, which is no big deal because z's are constant and z are not in any of these values anywhere in there, so it's fine. It can kind of go wherever. All right, now, what about theta and what about r? That's the trick. All right, so r is actually pretty easy. So if you imagine a spoke coming out from the pole, it's going to hit right here. So it's going to start at 0 at the pole and go out to this. So where is this? What's the radius of this? Well, this is a semicircle of radius 1, right? Because we can see it's 1 minus r squared. That's r squared, right? So we know that this is radius 1, right? R equals 1. Okay, so I know that I'm going from 0 to 1. No problem. So theta, right? That's the trickiest bit. We can see that we start here at theta equals 0. So we just need to figure out what angle this is and we'll be happy. Well, remember that we know the equation for that line. We know that x equals the square root of 3y. Okay, now if I want to bring the square root of 3 over, that's 1 over the square root of 3x equals y, which means 1 over the square root of 3 equals y divided by x. And you might be thinking, why are you doing that? Well, because there's a conversion formula. The tangent of theta is y over x. So I know this is the tangent of my angle, theta. So that means that theta is the arctangent of 1 over the square root of 3. And at this point, I'm very glad that I memorized my unit circle, because that would be pi over 6. Pi over 6 has, the sine of pi over 6 is 1/2. And then the cosine of pi over 6 is the square root of 3 over 2. And so if you took the tangent, which is sine over cosine, that would be 1 over the square root of 3. Ta-da! All right, so it's pi over 6. And I know I'm in quadrant 1, so I'm good, right? This is all great. If I was in a different quadrant, I'd have to fiddle around and figure out what relationship it has to pi over 6, but you know, it'd be over at the other side, like 5 pi over 6 or something like that if I was in quadrant 2. But I'm in quadrant 1, so we're good. All right, again, we can use our trick, right? Theta is nowhere anywhere in here. Theta is not involved. So I can just cross off my thetas and put a pi over 6 in front. Done. And while I'm at it, I can find this. This is r times r, which is r squared. So I'm going to integrate r squared with respect to z. So I'm going to have the integral from 0 to 1. The integral of r squared with respect to z is r squared z. Z is going from -1 to 1. So I'm doing 2 steps at once there. dr. So I did my trick and pulled the pi over 6 out, and I kind of simplified this in my head a little bit, and I got r squared z. So now I'm going to put 1 and -1 in. So this is pi over 6, integral from 0 to 1. And that's r squared times 1 take away -1. 1 taking away -1 is 2. dr. Okay, well, I could pull the 2 out. It could actually be written here, right? Because wherever, right? So let's just make a note, right? 1 take away -1 is 2. Right? That's where that's coming from. Okay, so 2 pi over 6 is in front, which we all know is pi over 3. And then we integrate this, which is r cubed over 3, and we're going to take that from 0 to 1. I'm doing this one in my head because I don't need maple. This is easy. So putting in 1, that would be 1, right? So this is pi over 9, right? 1/3 times pi over 3. Okay, so let's double check me with maple, just to make sure I did it right. There's the polar piece again, if you wanted to look at it in maple, right? There it is. It's that section that you're looking at. And then sure enough, this is my original integral, right, which got me pi over 9. And then there's my latest integral, which gets me pi over 9. That way I've checked my answers with myself, so I know my original integral and my last step are the same, so I know I did the middle steps in between correctly, and we're all set. Now, I didn't have any units because this didn't have a context with it. If there was going to be some kind of context, it would probably be density. This would be a density function in here, and then this would be a mass that we'd end up with. That's the most common example that we have for an application for a triple integral of a function. But again, it didn't give us anything, and it didn't give us units. And there are other ways to think about these things. But those are the ones that we use.